But we'll get started. This is our booklet on calculus. What you'll have here is a bunch of examples. We do some review today, and we're going to look at the first part of calculus, which is limits. So the idea of a limit is something that you get close to. And you've seen limits in some senses before. For example, on geometric sequences. Do you remember adding up an infinite geometric sequence? For example, right now let's say I'm about 16 tiles away from the wall. If I walk half the distance, I'll have walked 8 tiles. If I walk half the distance again, I'll walk another 4. And then half again, I'll walk 2, and I'll walk 1, then I'll walk a half, then a quarter, then an eighth. If I keep cutting the distance in half forever, I'll never get to the wall. Because whenever I get close to the wall, there'll still be a distance left, and I only walk half of that. But we've seen in geometric sequences, if you added up all of those numbers, 8 plus 4 plus 2 plus 1 plus a half, and so on. If you did that forever, we say it's equal to 16. And that 16 would be the limit, something that we can get arbitrarily close to. Because if I keep cutting the distance in half, I get closer and closer and closer to it.
But you never actually get to 16.
But I never actually get to 16. So we also have limits. Sometimes we've seen limits in our graphs, like an asymptote. You know, a graph might approach an asymptote at 0, meaning it gets closer and closer to it, but never approaches it. Throughout the course of the year, we look at 2 branches of calculus. The first part that we do is differential calculus, and then later we do integral calculus, which is basically working backwards. Now, integral calculus was sort of what was looked at first. Integral calculus, when we do it, it'll look at areas under curves. And this idea was already known to the Greeks way back when. Archimedes was studying stuff. They would call it something called the method of exhaustion. And we say that integral calculus started way back then. Differential calculus is more associated with Newton and Leibniz. What's interesting is these 2 scientists sort of discovered or wrote about calculus at relatively the same time. Now, back then there was no internet, so it wasn't like if someone discovered something, they posted it and then everybody knew in the whole wide world. So even though the years might be off by like 5 years, 10 years, they really had no knowledge. So they're both credited with finding or discovering calculus at relatively the same time. Now, if you grew up 100 years ago and were studying calculus in Germany, all those textbooks would say that Leibniz discovered calculus. And if you were studying calculus in England, all those textbooks would say that Newton discovered calculus. So it's kind of discovered at the same time. And calculus is concerned about rates of change. And so slopes that we've done in the past is a rate of change. As you go 1 to the right, you go up 3, and so on. So, to start off, an idea, and previous to doing limits, we need to revisit some of the skills that we already know. So let's start off with some easy ones, some things that you've done already. Factoring trinomials. This is the most difficult, easy factoring I can think of. Okay? Try it. Check it. Why did I pick this one?
Because it looks like it can be solved nicely with 4 and 6.
Did you think of 6 and 4 first? Okay. But it doesn't work with 6 and 4. But it works with 12 and 2. So plus 12 minus 2. Then we had factoring with a common factor. Again, no problems here. You can take out the common factor of h Oops, minus 1. And then we're left with a binomial inside. Can we factor that one further? No. You could try, right? You could set it up and say, if I could factor this, and one of the things when you're factoring, whatever, I mean in English, some of you come from French immersion, but in English we use this acronym called FOIL. If you're coming from French immersion and have never heard of this before, we use this because when you multiply something out, you multiply the first terms. And so if it were possible, the only possibility for our first terms would have to be 3h and h. Your last ones will always multiply to this one. So the only way I can get 1 is if it was 1 times 1, if I'm using whole numbers. Now, no matter what I put in here for plus or minus, the outside and the inside have to make 7. And we can probably see in this case that it's never going to make 7. So this one is not factorable beyond this. Just a show of hands, how many people are coming from French immersion? This is their first math class in English. So if you ever have like, how do you say that in English? Or if you have any questions like that? Yeah, and then there's some of the ones that are bad, right? Like reciprocal in French is inverse, and inverse in French is reciproque. So it's like totally messed up. But other than that, most things are quite similar, and sometimes the English words are easier to figure out than the French ones. So we call this a difference of squares when both the first term and the second term work out perfectly, and one would be plus 5 and one would be minus 5. So no problems up till now. This is all review. So review, not too exciting. Let's factor things a little bit messier. Let's start to do stuff like this. This is probably something you haven't seen before. Factoring something with negative exponents or fractional exponents, this looks different than what we've done. So what we're going to do is we're first going to use the idea of a common factor and factor out the smallest exponent as a common factor. In this case, the x to the minus 2. If I took out an x to the minus 2 out of this whole thing, what would be left? What would I have to multiply an x to the minus 2 by here in order to get a 1? An x squared. So that's kind of different. And if I've done that, I can now look at what's left. And this factors nicely. To x plus 2 and x plus 3. So here's one for you to try. If we take out the x to the negative a half out in front, and I'll do that first, that would leave me with 3x squared. Remember, when you multiply these, multiplying exponents means you add the exponents. The bases are the same in your multiplying. So can you see that 2 plus a negative a half gives me 3 halves? And if I factor out an x to the negative half here, negative half times just an x to the 1 would give me x to the positive a half. Minus 45, because we factored out that x to the negative half. Now you might also notice, and some of you did this already, is you saw that there was a 3 in common. So that 3 could have been factored out right away at the beginning as well. Which leaves us x minus 5, x plus 3. Now that's something new with factoring. Here's something that we'll see if you remember from your grade 12. Do you remember how to factor these ones with an x cubed? Where you have to use the factor theorem and the remainder theorem? Now the key number that you're going to be looking at here is the last number. So with the factor theorem and the remainder theorem for factoring this, you're going to look at factors of 10, which could be 1 or negative 1, and 10 and negative 10, 2 and 5. And you're going to plug those in to see if you can get something equal to 0. Now usually mental math-wise you start with 1 and negative 1. If I plug in 1, what happens? I'd get 3 plus 4, which is 7, minus 9, minus 10. That's going to be negative 12. That's not equal to 0. That tells us that x minus 1 is not a factor. If I plug in negative 1, that would give me negative 3 plus 4 plus 9 minus 10, and that is equal to 0. So that tells me x plus 1 is a factor. So the remainder theorem says when you plug in a value, whatever answer you get is your remainder if you were dividing by that value. So for f of 1, that means if I divided this by x minus 1, I would get a remainder of negative 12. Since my remainder is not 0, that means x minus 1 is not a factor. But when I plugged in negative 1, I got a remainder of 0. That tells me that x plus 1 is a factor. So if I wanted to factor this completely, the next thing that I would do, a review of synthetic division, bring the 3 down. So we multiply, so here I multiply this, that'll be negative 1, add, multiply again, and add. What we get with our synthetic division means that our original function, f of x, has now been partially factored. We know that x plus 1 was the factor, and after dividing by x plus 1, we're left with 3x squared plus x minus 10. And then to factor this completely, we would have to check if we can factor this further. If we could factor this further, the only way to get 3x squared would be 3x and x. To get 10, could be 5 and 2 or 1 and 10, but I need it to work out to get 1 here in the end. If I put a 2 here and a 5 here, can you see the outside will make 6? The inside would make 5 if you were multiplying this out. If I wanted to get a plus 1, I would need a plus 6 and a minus 5. And it factors completely. If you have other techniques for factoring, they're fine. But eventually we like to try to factor things directly if we can. Okay. We don't do a lot of factoring using the factor theorem and remainder theorem from grade 11 or grade 12, but I thought I'd bring it up just to look at it. We do a lot of factoring because when we look at limits, one of the strategies that we have for limits is can we factor something, because that can make your life easier. Oh, I put a comic. Yeah.
Wait, you're scary?
Don't I look scary? Okay. Here's some factoring that you probably didn't see in grade 12, and yet it is used a fair bit in universities. Differences of cubes and sum of cubes. Now, you could use your factor theorem and remainder theorem to figure this out, but these will be two formulas that we're going to have for difference of cubes and sum of cubes. So for difference of cubes and sum of cubes, some of the things that you can sort of do to help you figure these out. I mean, with x cubed minus y cubed, it starts with an x minus y. With x cubed plus y cubed, it starts with an x plus y. If you were going to multiply this all the way out, can you see that you're going to need an x squared there, so when you multiply the x by the x squared, you'll get an x cubed. You're going to need a y squared at the end, so when you multiply your minus y by the y squared, you're going to get a y cubed. And you can see what sign this needs to be, because a negative y times a positive y squared will give us a negative y cubed. Now, when everything else gets multiplied through here, just as we're watching it, can you see that here when I multiply this times this, I would get an x squared y. And when I multiply this times this, I would get a negative x squared y. And those would cancel out. If I multiply this times this, I'll get a positive xy squared. And when I multiply this times this, I'll get a negative xy squared. So if you would multiply and distribute everything here, everything would cancel out except for the blue, which is the x times the x squared, giving me x cubed, and the green, which is the y, negative y times the y squared, which would give me negative y cubed. Can you see the same thing is going to happen here? This will give me x cubed. This one would give me y cubed. If I multiplied this x times this, that would give me negative x squared y. And here I have plus x squared y. Similarly here, I'd have positive xy squared. And there I would have negative xy squared. So sometimes we're going to try to memorize things and it's not going to work. Sometimes you have to actually figure things out throughout it. So maybe you remember the beginning had an x minus y, but you don't remember what went after that. This is one way to sort of figure it out and recreate it. So maybe you recognize the 8 as 2 cubed. So that means we could factor out an x minus 2. We would get an x squared here, a plus 4 there, and a plus 2x there. Try the next one. So again, you see sort of as a preliminary step, I recognized it as a sum of cubes and I rewrote that second number as what it was cubed. So to recognize that 27b to the 6th, that's the same as 3b squared all cubed. And then it's a matter of saying, okay, so then it would be a plus 3b squared. Here I'm going to need my a squared for my a cubed. Here I'm going to need 9b to the 4 to get 27b to the 6. And then both of these get multiplied together in the middle. in this case with a minus sign. Again, what is our factoring most often more like? We most often get ones like this with numbers and one simple cubed. But it just shows that we could do it with extended numbers as well. In grade 11, you had to rationalize the denominators whenever you had a square root in the bottom. And you might remember sometimes having a binomial in the bottom, such as square root of x plus 3. And we have this word, I'll highlight it here, it's a good definition. The conjugate. And the conjugate is just the same binomial with a different sign in the middle. And whenever you multiply a binomial by its conjugate, it's a difference of squares. And what happens every time you multiply something that's a difference of squares? The first term gets squared, the second term gets squared. And so what this does is it gets rid of all square roots, because you're squaring the first term and you're squaring the second term. And that rationalizes the denominator. Now, all of these skills that we're doing right now, that are somewhat reviewing things that you've done in the past, are going to be skills that we're going to use when we try to find limits. So we'll see that coming up, but right now we're just practicing some of those skills. And one of those skills that's going to be important is rationalizing. Sometimes we're going to rationalize a denominator. Sometimes we're going to rationalize a numerator. So to recognize that we have a square root that we can multiply by the conjugate, because when we multiply by the conjugate, the bottom becomes a difference of squares. And so it will be, and I'll write it out like this, it'll be this one squared minus this one squared. That's what happens every time you multiply two conjugates together. On the top, if I distribute that 2, I'll get 2 root x plus 3 plus 4. Now, if I actually simplify the bottom, this is going to be x plus 3 minus 4, which just simplifies to x minus 1. So again, there is a couple there for you to try. Now, most of you probably wrote your answer like this. One thing you'll often see in the textbook is after they simplified, they factor completely. So they might, after multiplying it all out, decide to factor out the 5 again. So you might see that in the textbook, because this textbook, all of the answers at the back of the book are always in simplified form, and that often involves factoring completely. Now, in the next one, start out the next one, and when you rationalize the numerator, when you're working on the denominator, don't multiply it out right away. Keep it as two separate things and see if you can see why that might be helpful. Simplify your numerator, but don't necessarily multiply your denominator out on your next one. So on this one, we rationalize the numerator, and if we didn't multiply out the bottom, we notice something special. There's an x minus 16 on the top, an x minus 16 on the bottom, and those would simplify, and you'd end up with 1 over the root x plus 4. Now, why is this helpful? Well, if this was a graphing question, if this was equal to y, and you were graphing it, you might remember from last year that any time you have a factor cancel out like that, there's going to be a hole in that graph. Okay? And how do we find the coordinates of that hole? Well, we know the non-permissible value is 16. That's what's not allowed. But after it simplifies, you could plug 16 back in, and you would get 1 over the square root of 16 plus 4, which is 4 plus 4, 1 over 8. So this would have a hole, if you were graphing, at 16 comma 1 over 8. That's connecting it to what you did in grade 12 with graphing these things and finding out what happens when a factor cancels out with another factor. What we're going to be doing in limits is limits are concerned about what happens when you get close to non-permissible values. So in this question, we'd say, what happens when you get close to 16? What is this equal to? Well, right now, the way this is, you can't figure it out because you can't plug in 16. But if we simplify it, we can plug in 16. In fact, we get that hole. We say when you plug in 16, you get 1/8. So we're going to find out in this question with limits, the question would be, what's the limit as x gets close to 16? We're going to be able to say as x gets close to 16, this gets close to 1 over 8. And that's what the limit of this expression would be. So that's where we're leaning towards, and this is one of the examples that really shows it. All right, last one, I'll put it up so you can check how you did. Just look at the green for now. So if I was going to rationalize the numerator here, I write the conjugate on the top. When I multiply that out, on the top becomes x cubed minus 1. Once again, I didn't multiply out the bottom, because usually you like to keep things in factored form, because it might help you simplify. In this case, the top is a difference of cubes, which we learned earlier. You could factor it, and then something nicely simplifies. That's going to be a goal that we're going to have. Compared to last year, this would mean this graph, if you were graphing it, would have a hole, and that's going to be connected to the limit. We don't normally go this fast, but it was shortened periods, so I apologize a little bit for that. A little bit. Still wanted to get this done. This is out of your textbook if you would like to practice.